All right, welcome back for part 2 of velocity of a softball. Last time we had just figured out the horizontal and vertical components of velocity, each at 32.16 meters per second. So 32.16 meters per second up, 32.16 meters per second over, for a grand total at the 45-degree angle of 45.48 meters per second. Okay, so let's head up to the top and check out number 5. Number 5, how much time will the ball be in the air? How long will the ball be rising? How long will the ball be falling? Okay, so let's see, for time in the air going up, I know that this is controlled only on the vertical, right? Horizontal stuff does not affect how long it's in the air. It's only how far up and how far back down, because horizontal and vertical are independent. So I'm going to start by trying to identify some needs and givens here. Let's see. So I need time. And specifically, I need the time of the fall, right? I mean, technically, I need the time in the air, the time rising, and the time falling. But I know right off the bat, the time rising will be the same as the time falling. And if I add them together, that'll give me the total time in the air, right? Rising plus falling is the total time in the air. And they have to be the same because it's the same distance and the same velocities. Okay, so I need the time of falling. I'm given, well, in this particular question, I'm not given anything. There's no numbers in this question. So I got to look at some of the previous stuff and think about, what do I know about the vertical? I don't know how high it's going yet. I just figured out in question number 4 the vertical velocity. So I do know that that's 32.16. So I know that the vertical velocity is 32.16 meters per second. And then there's one other thing that I always know about things that go up and down, and that's the acceleration. I know that the acceleration due to gravity is always 9.8 meters per second squared. Okay, so I need the time. I've got velocity and acceleration. So I could use my acceleration equation. So if I look on my physics everything sheet, I'm going to look for an equation. I'm going to run down the equations line here and see if I can find an equation with time, velocity, and acceleration. And I found one. It is acceleration equals the change of velocity over the change of time. All right. So I know that my vertical velocity is how fast it comes off the bat. When it reaches the very, very top up here, right before it starts falling, how fast is it going? Well, it's going 0, right? It goes up, 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 velocity's up, stops, and then down, 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 velocity's down. But it has to go from up to down, has to go through 0. So at the very top, velocity is going to be 0. The vertical component of velocity is going to be 0. So my change of velocity, I'm going to rewrite this, is my vertical minus 0, because that's what it's going to. So I could write 9.8 meters per second squared equals the change of velocity, 32 down to 0, is a change of 32.16 meters per second over the time of fall. Okay, now to solve for time of fall, I'm going to multiply time of fall by both sides. Okay, that gets rid of that on that side. Now I have time of fall times 9.8 equals 32.16. To get rid of the 9.8, I have to divide both sides by 9.8 meters per second squared. Divide by 9.8 meters per second squared. That will cancel there. and leave me with the time of fall is 32.16 divided by 9.8 meters per second squared. So the time of the fall is equal to, I'm going to use my calculator, 32.16 divided by 9.8, 3.28 seconds. 3.28 seconds. Now, technically, the starting stuff that I had was only in 2 digits, so I should keep it as 2 digits. So I could say that's pretty much equal to 3.3 seconds, but I'm fine with leaving it 3.28. All right, now let's go back and read the question. How long will the ball be in the air? How long will be the ball rising? How long will the ball be falling? So I found the falling time as 3.28 seconds or 3.3 seconds. Now I mentioned at the beginning, I also know that the rising time is going to be the same, right? It's also going to be 3.28 or 3.3 seconds. And then if I add them together, that would give me my total time in the air. Time up plus time down gives me the total. So the time in air is equal to 3.28 plus 3.28 is rounded to 6.6 seconds, or precisely 3.28 times 2, 6.56. So technically it's 6.56 seconds. All right, so I'm going to say these ones are my answers, and that plus that, right? Time of fall is 3.3 seconds. Nice. But I'm going to keep that 6.56 in case I have to use it later on, because I want to use the most precise value when I use it in the future. All right. Now for number 6, how high will the ball go? Let's see, how high is a distance, right? And it's a height, which means it's a vertical distance. So I need now the distance vertical. I am given, well, I just found the times. So I know the time. And vertically, I also know the vertical velocity, and I know the acceleration due to gravity. So I could go back, check my physics everything sheet, and I see that I just added something for vertical distance, right? So my vertical distance equation was vertical distance equals 1/2 acceleration due to gravity time of the fall squared. Okay, so now I know specifically which values I need. I don't need the vertical velocity. That's not in the equation. Acceleration due to gravity is equal to 9.8 meters per second squared. And the time that I want is the time of the fall, just one direction. And that is 3.28 seconds. Okay, so now it's just a matter of plugging in my values. I have the vertical distance is equal to 1/2 times 9.8 meters per second squared times the falling time, which was 3.28 seconds squared. So I'm going to start by squaring 3.28 squared, okay, times 9.8 times 1/2, which is 0.5, and that gives me 52.7. So my vertical distance is 52.7 meters, but because I can only take it to 2 digits based on significant figures, that'll be 53 meters up in the air. Okay, so I'm starting to get a little bit concerned. 53 meters is like 170 feet. That's a 17-story building. That sucker is a moonshot. That is way high. So that'd be a very, very high hit. But, you know, not outrageous, kind of outrageous, but we'll see. Okay, but that is how high it should be going. All right. Then for number 7, and you'll notice for how high, because it's vertical, I only used vertical components, right? How high is vertical, so I have to only look at vertical up and down stuff. All right, now for horizontal. How far horizontally will the ball travel? So that's also a distance, but it's going to be, I need the distance horizontal. So what do I know horizontal? Well, I already calculated in number 4 the horizontal component of velocity. The horizontal velocity was 32.16 meters per second. Okay. I've also already found a time. I found a few times. So now I got to think about which time matters. Which time is how long the ball is moving horizontally. So if I think about the ball, I hit the ball, it goes up, it's moving horizontally. It comes back down, it's still moving horizontally. So I need the total time in the air because the ball is going up and down, but it's moving horizontally the entire time. So I'm going to take the whole total time in air, right? That's going to be my full horizontal time. And that was 6.56 seconds. All right. Now I have an equation for horizontal velocity. And if I double check and look for an equation that relates distance, velocity, and time, the equation I can find is velocity horizontal is equal to distance horizontal over the time in the air. Okay, horizontal time. All right, so I will plug in my values there. Velocity horizontal, 32.16 meters per second equals the distance horizontal, that's what I'm solving for, divided by 6.56 seconds. To get horizontal distance by itself, I'm going to have to multiply both sides by 6.56 seconds times 6.56 seconds. Those will cancel, leaving me with multiplying those together. 32.16 is the horizontal component times 6.56 seconds, 211 meters. So I find the distance horizontal is equal to 211 meters. Technically, I should round to 2 digits. So that would be distance horizontal equals 210 meters. That third digit should disappear because of significant figures. Okay, so 210 meters. Multiply that by 3¼ meters, or sorry, feet in a meter. That puts me around 700 feet. Oh, okay. So 700 feet, that would be like the world record for hitting a home run. A really big home run in Major League Baseball would be like 450 feet. If you're going over 400 feet, that's a good sized home run. 500 feet is crazy. I don't know that anybody has ever hit a 600-foot home run. And this one is well over 600, going at like 700 feet. So we have a problem. I'm going to go ahead and skip down past number 8, and let's try to figure out what's the problem? Why doesn't the ball actually travel that far in real softball? So how is this problem different from real life? Okay, so let's just kind of detail some things, some assumptions that we made. So the first one that I can think about is the pitch speed seemed right. the bat speed seemed right. We made an assumption about how it was hit. So we assumed that it was a fully elastic collision. So we know, however, that the collision between any two objects can't be 100% elastic because there's friction. So the collision is not really 100% elastic. And that's the first thing. The second thing was when we said it was an elastic collision, we treated the bat as a non-moving wall. We just said the bat just moves through no matter what and sends it off with the perfect exit velocity. That doesn't happen either, right? We know that if you actually hit a baseball, you get recoil on the bat. The bat pushes back against you because of conservation of momentum. So we should say momentum should be conserved in real life. So like bat should recoil, which means it won't just move forwards perfectly. Okay, so that's another one. Then we had a 45-degree exit velocity. That's possible. That is possible. That's definitely feasible. But there's a big factor that would be getting in the way that we are not including. And that big factor that should be getting in the way that we're not paying attention to is air resistance. In real life, the air is going to push back against that ball and it's going to slow it way down. So instead of going all the way out and following a perfect parabola, it would go out and then it would kind of die and come straight back down. Not straight back down, but more vertically down. So air resistance would reduce the distance by a lot. And then another piece, I guess the cousin of air resistance and the cousin of 100% elastic collision would be friction. All right, friction's kind of accounted for in air resistance. It's kind of accounted for in that elastic collision, but I'll add it its own thing just to note that like there should be some friction. One other piece, I guess, is when we said, I took the total velocity, the 45.48, and then I just said it's leaving at that angle, at the 45-degree angle. But if I'm putting some of that energy, I could do that. You might lose a small fraction from the trigonometry of coming in horizontally and then leaving at the 45-degree angle. So that math is a little bit complex, but you could lose a little bit due to that angle piece. All right, so that's number 9, and we're gonna kind of leave it there for now. If you can think of another one, see if you can think of another one and put it in the comments here. Why else would this be not perfect? All right, and then finally, number 8 is our most challenging question, in my opinion. It's also a really interesting one. So if the softball has a mass of 7 ounces and impacts the bat for 0.01 thousandth of a second, what is the force of the bat on the ball? So now I need force. And specifically, it's a force of an impact, right? It's a connection. So force of impact. I am given a mass of 7 ounces. So I'm given mass is 7 ounces. I am given a time of 0.001 seconds. That's the time of impact. And then I have a bunch of information about velocities and all that stuff. Okay, so my force of impact. So for starters, I'm gonna look for the right equation. And I need one that has force, time, mass. And I think the one to go with is mass times the change of velocity is equal to the force times the time. Okay, so the force of impact times the time of impact. And then I'll need to figure out my change of velocity as well. So Actually, I'm going to do the change of velocity in just a second. All right. So let's start with the mass and say the mass is currently in ounces. That is a non-normal piece. So I'm going to change it into kilograms. So to change it into kilograms, I'm going to do a couple converters. First, I can go ounces into pounds. So I have it ounces on the top. So I'm going to need to put ounces on the bottom and then pounds on the top because I know that there are 16 ounces in 1 pound. Now, that gets rid of ounces and leaves me with pounds. Now I need to get rid of my pounds. So I'm going to put pounds on the bottom and turn them into kilograms. And I happen to know that there are 2.2 pounds in 1 kilogram. Okay. So that, I have 7 on top, 16 on the bottom, 2.2 on the bottom. So I'm going to do 7 divided by 16 divided by 2.2, 0.1988. That's 0.20, right? 0.2 is my mass in kilograms. Cool, 0.2 kilograms. Great. Okay, the next part is I now need my change of velocity. And to find my change of velocity, I'm going to draw a little diagram. So I'm going to draw out, here is my batter, and she has the bat, and she also has legs. I'll include legs for her. Here is my pitcher, also with legs. So pitcher takes the ball and throws the ball towards the batter. Okay, so this is my incoming velocity. Is, that was the pitch, right? So the pitch was 30.48 meters per second. So she pitches it in at 30.48 meters per second. Okay, then there's a collision, pew, where the batter hits the ball, and the ball leaves with a velocity of 45.48 meters per second. Okay, so 45.48 meters per second. Okay, so we could do some trigonometry and figure out, the components of that and, how much change of velocity we count and don't count, but I'm just going to treat them as if they're on the same plane and say 30 in, 45 out, boom. All right, so I'm going to call this one where it's leaving my velocity final. I'm going to call this one where it's coming in my velocity initial. That was the beginning. And then I also know that they're in different directions. So one's coming in and one's going out. So because they've changed direction, I have to make one of them negative, right? I can't have two things going opposite ways and say they're both positive. So I'm going to make my initial velocity negative. So this is going to be negative 30.48 meters per second. Okay. Now I can say that the change of velocity is equal to velocity final minus the velocity initial, which is equal to the final velocity was 45.48 meters per second minus the initial velocity, which was negative 30.48 meters per second. So the change of velocity is going to be 45 plus 30. Okay? So it'll be 45.48 plus 30.48 for a grand total of 75.96 meters per second. Now you'll notice that's bigger than either of my other two because it's changed direction. Remember, bouncing leads to a greater change of velocity or a greater force, and that's basically what we have here. We have a bounce. So I should end up with a bigger number than either of my other two numbers because it's changed direction. All right, now I have this piece. I am going to, oops, not do that. So now I've got all of my parts. They're in the right units. I'm going to use my m delta v equals ft. And I'm going to straighten this and not ruin it. There you go. Okay. So I'm going to go back and just say I'm going to move this over. M delta v equals f t, or change in time. Okay, the mass was 0.2 kilograms times the change of velocity was 75.96 meters per second equals the force of the impact, that's what I'm solving for, times the time, which was 0.001 seconds. Okay. To get force by itself, I'm going to divide both sides by 0.001 seconds. Divide by 0.001 seconds. That will cancel those guys, leaving me with force. So it's going to be 0.2 times 75.96 divided by 0.001, 15,192. 15,192 newtons is equal to the force. And since I'm rounding to 2 digits, that's equal to 15,000 newtons. That is a lot of newtons. Okay, so 15,000 newtons, if I wanted to compare that to pounds, I could divide by like 4.45 newtons in a pound. That's 3,400 pounds. So just for a comparison point, that's about equal to 3,400 pounds. Now, that 15,000 newtons seems like a crazy big number, right? But I think the way to compare it would be to say, all right, let's put your knee in place of that ball. Would you rather have your knee hit as hard as the person can swing for a home run and hit you in the knee with that softball bat, which is made of aluminum? Ow, I think it would break your knee. Or what else is 3,400 pounds? Like a pickup truck. Or have a pickup truck run over your knee. Both are bad, right? Both probably breaking your knee. So I would say, yeah, 3,400 pounds is a lot. 15,000 newtons feels like a lot, but it also feels possible, right? If you do a compare, which one feels worse, they both feel real bad. So that seems like a reasonable number. And just like that, we are all the way at the end. We have solved all the way through. Whew, way to hang in there. Good job. All right, so we're going to stop there. Make sure that you have written down all of these as well, and have a lovely rest of your day thinking about the motion of balls and other things in sports.